I hope you can hear me. Okay, so this came about because I'm in working with very high speed transfer technologies in my company. We ran against certain issues that kept on appearing again and again, and kind of we are trying to be a step ahead of our competition, because with better technology we make more money. And so we're kind of depending to be here at the cutting edge. And we're seeing some trends here that are kind of a bit disturbing. We have extreme fast fabrics, and they're getting faster and faster, but it seems that we are running into other things that make it very difficult to actually use the speed. And so I'm going to talk about, first of all, why this is. And then second, there's a section on the existing mechanisms to mediate the situation from various vendors. And then finally, I think when we're talking about what we could do in the RDMA world to actually make use of this in a kind of with a consistent API, and maybe come up with a new approach that allows us to orchestrate these new hardware features. So yeah, the general notion is that these things go too fast. And if you look at some of the presentations here, we're talking about QDR, we're talking about ConnectX-2. Both technologies have been discouraged and have been declared obsolete by the vendor. But they're still in use, and it seems that these speeds are actually useful, and we can't really go beyond that, even if we upgrade the hardware in these special use cases. And so I think the RDMA project in itself, what the UFA does, and has enabled, it was very successful. So much so that we actually get to these super high speeds that we can barely make use of in reasonable applications and reasonable hardware. And so I think we need to orient ourselves and see how we can solve these issues. So my company has stopped upgrading all InfiniBand fabrics because the new speeds don't make any sense. We have used QDR for years until we will get blackmailed by the vendor with saying that we no longer support this. So we had to upgrade everything to the newest technology, and now we are using EDR almost everywhere. But we can't really use the full performance, and one of the reasons is this mismatch to the processor speed and the memory speeds. And it seems also that the roadmap of the IBTA that you're seeing here seems to be slipping. We have HDR being deployed, and so it seems that we are now slowing down, because it seems that the adoption of HDR is extremely slow and extremely kind of in the molasses. The problem there is, can you actually use this? And the problem here is mainly the PCIe 3 barrier. This is it's a certain problem if you have an interconnect that has a 25 gig lane speed, and then you're entering a PCIe interface with a lane speed of about 8 gigabits. And so when you come into the system, one lane forks out into multiple lanes that go into your system bus. This used to be the other way around. The internal bus used to be much faster than any external links, but we now have the opposite situation. And this is certainly also one reason is because one of the major vendors for the processors has gone through some management issues and can't make progress lately too much in many areas. And that has also stopped, for example, for us, the deployment of new processors, because there isn't much of a change. What's the point? They're still using PCIe 3. We still have the same problem. So why would you use any new processors as well? So this whole thing comes to a standstill based on the processor technology. So if you want to actually get 100 gig into the processor, then you're needing lots of these precious PCIe lanes, for which only you have a few. And then maybe you can get a huge amount into the processor, but how can you get it back to storage? Back to storage requires another set of these PCIe lanes that are so precious, and you run out. So there's very limited what you can do in terms of the bandwidth that you can get in and out. And so the roadmap is really roadkill now at this point. I think we have stopped at HDR, and I think we are not going to go much further than that, because I think the HDR deployment that I've heard about are pretty minuscule. So the excess capacity is useful but only if you have specialized hardware situations. There are certain situations that are specialized where you can make use of the additional bandwidth that comes with very high speeds. But the higher they get, the higher the need comes about for specialized offload engines that can only, and they will only be able to handle that performance and that throughput. And the special offload software that mostly used today is GPUs and FPGAs to handle this overhead in terms of performance, because general purpose is no longer able to handle that. So in some ways we have been too successful. We have increased the speed beyond all measure, and we are now running against all other limits in the system architecture. And this comes back, one of the key things here is the PCIe woes. So PCIe 4 would double the data rate, and it was supposed to be delivered from, if you look at the roadmap, in 2017. It was not. And so we're still stuck on PCIe 3. And with that, we have these, the problem with the PCIe lanes, and we don't have enough capacity to get into the system to really do 100 gig or something higher than that. So EDR, actually, we can't use the full potential of EDR at this point, so why would we use a higher speed? And then there's all these rumors going on in the industry about PCIe 4. There was a rumor that Intel would be delivering something, at least a few lanes on a new processor this year. Didn't pan out. We're looking at 2020 maybe. Then there's rumors that AMD is coming out in the middle of the year with some PCIe 4 stuff. But then the processor will be inferior, so there's all these issues where you can't move forward and you're stalled on the bandwidth. And then the other issue in the industry is, in my industry, is that the PCIe latencies are so high that you actually, if you want to execute an electronic trade, you cannot afford to cross that boundary anymore. So we are not talking about PCIe anymore in our industry. We're talking about the PCIe barrier, because we can't get through it. You need to have devices before the PCIe that work independent of the main processor, because otherwise you can't compete. So the whole general compute paradigm for us becomes a huge problem. We can't do stuff anymore in the main memory that we used there. We need to move more and more to specialized hardware to handle these speeds. So it seems that the whole Intel general compute paradigm becomes more and more problematic as we move to higher speeds. And we're getting into very specialized hardware solutions, both for floating point calculations like the GPUs, or for specialized other solutions in terms of FPGAs in some cases. So this all gets extremely expensive and requires a huge number of people that have very specialized knowledge and very expensive to pay. So this kind of handcuffs you everywhere and constrains you the speed in which you can evolve your infrastructure. So then we also looked at OpenCAPI. There is an alternate development here with a 25 giga transaction rate per lane, so 3 times faster than PCIe. And the bright idea of IBM was to take the 100 gig transceivers, which is 25 gig, and use them for the internal bus. Hey, hallelujah, yes, right. So if you can't keep up with the external networking, then use it for the internal networking. Why not? At least you have the same speeds. So that's only in Power 9, and so we would have to kind of rebuild all our software for another architecture, which killed the whole thing. And then the shocking development in terms of InfiniBand, which we always thought was the fastest technology that was going to be available in terms of networking, is now the development of NVLink. And suddenly we have a proprietary link between NVIDIA GPUs that runs at 300 gigabytes per second, which is much higher than any of the InfiniBand speeds. But this is also dependent on very specialized hardware and comes with a paradigm that's not general purpose compute anymore. And so that is actually one of the, I think, the key problems right now for throughput and for high performance computing. We can't get beyond the barrier, and there is, I know that a lot of startups are trying now to solve this problem with new processor technology, new interconnects. So in the last couple of years, this has been quite fertile ground. But none of them, I think, was going to be available to 2020 or 2021. Then the issues with memory bandwidth. So we keep on also, in terms of the processor, adding more memory channels. We are unable to significantly increase the bandwidth to the memory channels now. So adding more memory channels means more pins to the CPU, means more complex routing, and also there we run against a limitation. So AMD has beat Intel by just adding 2 more memory channels and therefore have additional capacity. So memory channel gives you maybe 20 gigabytes per channel. So Intel can do 120 gigabytes per second. AMD can do 150. So there at least is something good. And the total throughput to memory is still sufficient to dump all stuff that will be coming in via PCIe into memory. And that is certainly the case as long as PCIe constrains the stuff that you can get into the system. That's certainly good. The problem is if you go to individual threads now, let's say you want to do, in a core, inspect the data stream. You can only get about 12 to 20 gigabytes per second into a single core. So if you have a 100 gig Ethernet stream or something like that, or a 100 gig InfiniBand stream, you cannot analyze all the packets in one core anymore. You must have some mechanism to distribute the packets across multiple cores. And now you have the problem of synchronization and keeping state onto which packets is currently being processed. And so you need to actually redesign the network flow in such a way that it is limited so that a single processor can handle the data. That makes the design of the network protocol and the network communication a bit difficult and complex. And I think that's unnecessary if we would have just some way to get beyond these problems here. Then we have new memory technologies like GDDR and HBM. They have much higher bandwidth than the existing processor memory DRAM that we have, DDR4. And so I think one of the elements that enabled the NVIDIA high-speed NVLink is the use of this high-speed memory. Otherwise, you couldn't really get this data in and out of the GPUs. So one thing here is also, in terms of the processors, we probably should be looking forward to some kind of a change in paradigm where we have much higher memory bandwidth from these processors. So then the processor bottleneck. This is actually an old issue that was mostly solved by the RDMA stack. And so I'm going to talk about the classic network stack that we're actually bypassing with RDMA and what has been done on that level. And then about the RDMA NICs and what is happening on that level. So Facebook had an issue with high-speed networking. They tried to go to high-speed networking, but I didn't want to use RDMA. I talked with the architect, and he was very adamant, never going to do RDMA. So what they did is they paid some money to Red Hat, it seems, and Red Hat started to pay a developer, Jesper Brouwer, to optimize the network stack for high-speed processing. So I had to rework some of my subsystems in the kernel to accommodate his stuff, and added some gang processing there, here and there. But he could only get to about 10 gigabytes per second, and actually that was pretty good, I thought, because you have a latency budget of about 1.2 microseconds to process a packet before the next one arrives at these speeds. And if you want to keep up, you have to do this. And so what you can do with 1.2 microseconds is you can do basic packet routing. So in software, you are able to basically classify the packet and push it onto a certain core. And then it would be spread over multiple cores. But the kernel could still keep its key role as a routing function in the network stack. But then now, let's say you have a 100 gigabit link. And now you have 120 nanoseconds per packet. At that point, that's all. You have the time maybe to fetch a cache line if you wanted to, or do some processing. So at that point, you cannot really do anything reasonable anymore with the processor. So if you restrict yourself to extremely large packets that go beyond the Ethernet specification, let's say you handle 10K at one time, and you violate the spec, then you may have enough time to process the packet. But with 100 gigabits, you must basically, if you want to use Ethernet frames, you must have a hardware mechanism to classify these packets and route these packets to various cores in order to process them. And so what has been done now in the standard network stack is there's a new technique called XDP, which allows you to register user space buffers with a socket. And so this is very similar to what we've done with RDMA. So a packet comes in, gets classified by something, could be the kernel, and then pushed forward into user space to an XDP buffer. The most recent development there is that we're using a kernel macro language called the eBPF to classify the packets. And some of the NICs now have begun to provide mechanisms to execute the packet classification in the NIC. So with that, you can do a similar thing to an RDMA NIC. The packet comes in, gets classified, and pushed into the XTP without kernel intervention. So at that point, you will be able to do some more advanced stuff here. But you basically have copied the RDMA methods that we are familiar with. And we have tied it up to the socket API. And this is Jesper's talk about how he tends to, if you look at the picture there, how he gets to 100 gigabits. There's a YouTube talk on this one. And I've had a lot of cooperation with him in the last 3 years to make all of this possible. So now the existing solutions, how do we deal with this? This is a normal OS stack NIC developments. As I told you, there's the XTP. But over the years, we've added basically more and more offload techniques in order to avoid the processor being involved in packet processing. This started with checksum processing, then packet aggregation and segmentation. So the kernel can give a 64K packet to the NIC. The NIC then chunks that into 1,500 byte packets that are conformant to the Ethernet specification. And then there's interrupt aggregation like NAPI. Then we have XTP, which does the hardware flow detection and direction to OS threads. And then we're getting full routing in hardware instead of software through these programmable redirectors. And what we also have done in the normal stack is per hardware thread queuing. So every NIC would provide a kind of a send queue for each of the processors in the kernel. This means you can simply put it into the local processor's queue and get the packet sent. The arbitration of the sequence of sending is handled by the NIC. With that, you remove all contention and you can send local packets directly without having serialization issues. And then we have also multiple virtual NICs that can receive different flows. And so NIC segmentation for virtual guests is pretty standard these days, I think. So we have flow segmentation also going on in the normal NICs. In many ways, some of the elements that we've done for RDMA NICs have been copied there. If you have an RDMA NIC, we have an implicit flow direction based on the QPs and where the QP endpoints sit. Then we also have added flow steering APIs to the existing RDMA semantics. So you can say, okay, certain types of traffic go to a certain QP. We have added packet classification logic to the NICs. So you can identify certain bit streams or bit patterns in a packet and redirect that to certain flows and QPs. Then virtualization support, the RDMA NIC can route packets within the system between various NICs. It becomes a switch, because now you can do RDMA transfers between different virtual instances of the operating system. And then a new thing is device local memory. The problem with PCIe exists, but what if you don't have to go through PCIe? So equip the adapter with some memory, and transfer from the network doesn't have to go through PCIe, it goes directly into the NIC memory. And then you can pick it up there with some transfer commands. So we're adding device local memory to circumvent that problem. We can't get to main memory, but at least it's in the system somewhere, and we can selectively inspect it, and maybe we can have some special code run on the NIC that inspects the packet. Then also there's peer direct connections. Another problem is going to storage. So NVMe over Fabrics works by having an NVMe device that does the storage, and then the NIC that does the reception of the data. And the NIC can directly talk to the storage device to put the data into the local memory buffers of the flash drive, so that we don't have to go through main memory, which is another way to circumvent the problems with capacities. And then one thing that I've seen is pretty, I think this is pretty new and very niche right now, is I've seen specialized development of specialized network elements that can process data at line rate. For example, there are certain chips that are used for switches that are put in there before the data reaches the switch, and they can do some primitive data processing in the chip. Like they can do timestamping, they can do VLAN tagging, they can do packet diagnostics, while the packet is not going through at full line rate. And maybe this can also do simple packet modifications in the future. And such specialized hardware could work with very high bandwidths regardless, because it does not contain any processing in a regular sense. It's just a dedicated element with a fixed functionality. So maybe those things could be generalized and made to work also on very high speed packets. But right now it only works for 10 gig. So, where are we going with this? So the far, maybe not so far future is how do we handle a terabit video stream, right? So you want to transfer a 3D picture or hologram, and the data rate there is about a terabit. And so I think that would be one goal to get to, and some people have said that they want to do this. So how can we do this? How can we actually make the RDMA subsystem able to be used for such a thing? This is also part of the exascale computing challenge, right? You want to have these high capacities. How do we move these massive amounts of data? And maybe we need a new hardware architecture in HPC. Certainly there are a lot of signs that this happens because the general compute paradigm is breaking down, and we have these specialized computing devices like GPUs. We have super high-speed networking like NVLink, and we have new types of RAM. So, and it seems that things are shifting away from the classic processors into these specialized devices. So the question then, of course, is how do we evolve the RDMA stack to deal with these issues? So in some way, we need to be able to handle GPUs and these other things to the RDMA stack. And what's happening right now is that NVIDIA is adding new components to the RDMA stack. All these vendors try to add new things to our APIs, and they're usually using side channels, and it's vendor-specific what's being added there. So the RDMA stack is an amalgam of various features and subprotocols that are vendor-specific. And the most egregious, of course, is the older one between the, I think, the UCX and the Intel version of doing MPI, which goes through different channels and therefore uses a different communication method. And these things are bolted on here and there and everywhere, and we end up with a pretty nice cheese with a lot of holes. And where it's very difficult to program for, because your application will be vendor specific and will no longer be transportable between different RDMA NICs. So if anybody has an idea how to come up with a new generalization to cover all these use cases and simplify it, that would be very helpful. And then I have some pipe dream here on the next pages. Maybe make RDMA different. So RDMA data may never reach main memory. Some data may go into the NIC, may go into the storage device. It may be some flow processing element that really doesn't have any storage. So in that case, it means both elements of an RDMA operation may be remote, actually. It may not be a transfer into main memory. It may be a transfer into the device's memory. What we currently do is we have specialized memory handles for the PCIe subsystem that signify that this memory segment is on a device, and so the transfer goes from the device from the NIC into the memory, as bypassing the PCIe. So in some ways we have that, but we haven't really formalized it, and we're not aware of that in any way in the RDMA subsystem. So. In that case, also, we're getting more to the functionality of a network controller rather than an API. So the role of the host CPU is depreciated as more to become a controller. And therefore, the RDMA command and the RDMA API must reflect that. We must be able, basically, to control remote devices that keep where the data is flowing through, where data is flowing to remote points. So it's more like a control language, maybe a specification of a network topology, how the data flows in the system. And maybe also we should be using programmable connections to make that possible. I know of devices in my industry where you can just hook up various devices and it just kind of does the cabling. And if you had basically an array of these devices with such a programmable wiring, you could use something like a specification protocol of a network to specify how the data flows for your special use case and how the processing elements will handle the data stream in order to optimally process that. So that ends up with being some kind of a software-defined networking the RDMA way, which is a bit strange. But I think we need to think about this and see how we address these things in the future. So the question is, where are we going with RDMA? Yeah, so how can we address these super high data speeds and these super high data streams that we hopefully will have in the future? So we want to see some 3D transmissions at some point, and maybe some other things where we can do much larger simulations than today. And in order to get to the exascale computing and beyond, we probably need to have abilities like this, and we need to be able to deal with specialized hardware and different architectures. And so that maybe require a lot of rethinking of the way we do things. That's it. Thank you. Questions? Anyone?
Can I please request to get walk to the microphone?
This is Venkat from Intel. Your first bullet is very interesting. I mean, RDMA doesn't necessarily mean that you need to write all the data back to memory.
Right.
So I think it makes sense to do some type of RDMA which actually could do the transformation, and the transformation could range right from writing nothing to writing a part of it, or doing some compute and writing the transform data. So perhaps we need to do something called RDMA-T or something, RDMA with transformation.
Yeah.
And some of this, I mean, of course, it's sort of also a pitch for our presentation at 11:30, but some of this we are targeting as part of supporting in OFI
Okay.
with extensions.
Okay.
Thank you.
Tom?
So you're basically saying we're doomed to building new hardware to take advantage of anything over 100 gigabits.
Yes.
I mean, that's really depressing.
Yes, it is.
You explore solutions. Have you started down that road? Are you building this stuff? Are you?
I cannot say anything about that.
Yeah, okay. Well, it seems to me that the protocols are probably okay,
Yeah.
right? And this is an implementation on the back end that's holding it back.
Well,
Would you agree with that?
No, if you want to do, for example, if you have these processors that can do 20 gigabytes per second, then you need to segment the network stream in such a way that it can be processed by these cores. Basically, the hardware influences the design of the communication protocol.
Sure.
Similarly, the NVIDIA NVLink is designed for these high speeds.
Right, but the protocol approach to that would be to use multiple queue pairs and sort based on some protocol level discriminator, right?
Yes, in some ways, if you don't go remote, yes. If you want to get the stuff into the local processor, and if the direction involves also going, maybe it can be redirected to a device, local storage.
Okay.
There's a lot of complications here.
Well, usually an SDN approach would use protocol tokens to do its, its sorting, if you will, its flow discriminator. So it seems to me that's there. But,
Okay.
But the bandwidth to actually deliver the data is what you're arguing is missing. So
I think the bandwidth is there, but the handling of in software or in hardware is very immature. And you end up with a lot of specialized solutions that are very expensive to support. So in some kind of way to structure this, I don't know how. I have never heard of the token approach. Maybe that's something, but someone ought to be thinking about this and come up with something that makes it workable.
No, I totally agree. I'm just trying to fish through a layer and figure out which way you're arguing we go.
Right.
But okay, yeah. All right, thanks.
Right. Any other questions?
Where do you get those 3D cameras at?
I have no idea. Maybe you can resurrect Atari. Okay, thank you.